So I'm going to do, I think I have two examples for you, and they both come out of the textbook. And I know you don't have your textbooks here because I told you not to bring them to school. So I'm going to talk you through what it says, and then if you want to go home and look at it again, then you can. You can at least write down the numbers here. This is example 19.2 on page 791. And it says that elemental mercury is a silver liquid at room temperature. AP stuff that gives you a whole backstory before you actually do anything. Its normal freezing point is negative 38.9 degrees Celsius, and its molar enthalpy of fusion is, and it actually tells you this, molar enthalpy of fusion equals 2.29 kilojoules per mole. Now, something to know, back in Chem 1 when we talked about the process of there's freezing and melting and vaporizing and condensing and all those things. Fusion is a change of state. Fusion means melting. We are absorbing this much energy to make this melt. That's what heat of fusion is. It takes 2.29 kilojoules per mole coming in, right, it's positive, in order to make this thing melt. So that's the first thing. It says, what is the entropy change of the system? Entropy, what letter is that?
S.
S, very good. So we want to know what is the entropy change, delta S, when 50 grams of mercury freezes. The reason we're looking at this example is because a similar question comes up in a few days on an AP question that we're going to go over. So normally delta H's are in terms of kilojoules per mole. Your S is in terms of joules per Kelvin per mole, right? They're all per mole. But this is not 1 mole. You don't always have to have exactly 1 mole. You could have half a mole and it would be, less than this number, right? So here's what we're looking at. Freezing is the opposite of this. So when we're freezing, delta H of freezing is the same number, but this substance is losing heat. Temperature is going down. It has to give away its heat energy in order to freeze. So the sign is the opposite of the sign of melting. So that's the first thing we really have to think of. And so it says plan this out. We can use the delta H of the freezing and the atomic weight of mercury to calculate Q. Then we can use Q to determine delta S. So here's what it wants us to do. It wants us to find the heat. We're going to relate these things. 50 grams of mercury. First thing we want to do is make it moles of mercury. And that means dividing it by your AP periodic table has a specific number. Not necessarily that one. It's probably 200.6, but I'm going to check it. 200.59. Okay. Same number. This is the molar mass of mercury. On the AP exam, when you're doing molar masses, a lot of times this give to you, which is really nice. But if not, use the numbers that they give you on this periodic table, and then just don't round them off until the end. So this is moles of mercury, and we're going to relate it to this. So for every 1 mole, actually this one right here, for every 1 mole that freezes, negative 2.29 kilojoules are released. Negative is releasing energy. It's losing energy. And then let's change it to joules because Q is typically in joules. Here's the conversion. And when you put this in your calculator, you should end up with something around negative 571 joules. So this is really the step that I wanted you to see, because you can change from one thing to another. You don't have to be exactly 2.29 kilojoules all the time. It could be more or less, and it all depends on the situation. How much reactant is there? How much product is there? That's the main part of what I want you to see. To find delta S, they do something that we haven't actually talked about. There is a formula that is in the book, but it's not on the AP exam sheet, and it's not in our notes, so it's not one that's going to come up again. So don't worry about it too much, but delta S equals Q over the Kelvin temperature. And so we're just going to plug in some numbers. Negative 571 joules. And the temperature they gave us in the question, and we kind of just breezed over it. Temperature was negative 38.9 degrees Celsius. Negative 38.9 plus 273. This has to be in Kelvin. 234.1 Kelvin. That's a negative 2.44 joules per Kelvin. This is really the part that I wanted you to see. Okay? And if you thought about it long enough, you might actually be able to figure this out. If you looked at the units for S, they were joules per Kelvin. You know, that's heat is in joules, temperature is in Kelvin. You could have figured it out. If this were the AP exam and you had to derive that in your head, I would say, move on to the next question. But this, not something that you really have to worry about. This is what I wanted you to see. The next one is example 19.6, and it comes from page 805. This one is your Gibbs free energy calculations, and this should seem a lot more familiar than the one we just did. Here's a reaction. and it's already balanced. They give us a delta H, a standard delta H. And they give us a standard delta S. Here's what the question says. Is the reaction spontaneous under these conditions? So this is a word that should not be said. What's the word? What's the phrase? Thermodynamically favorable. Textbooks are still using the word spontaneous. I have a textbook that was printed, its copyright date is 2018. It's still saying spontaneous. AP Chemistry has been really hating the word spontaneous since before that, but the textbook still says it. But if you take the AP exam and you write the word spontaneous, they're going to mark it wrong. So there's a big discrepancy here, and we have to be really careful on our end because they're less forgiving, so we have to be more careful. Is the reaction thermodynamically favorable under these conditions? When you're looking for thermodynamically favorable, you're probably looking for delta G. And a dead giveaway is that we have a delta H and we have a delta S, and we actually have a temperature, 298 Kelvin. These are the three things that goes into the calculation for Gibbs free energy. Here's one of the three formulas that's on your AP exam sheet. Delta G minus T delta S. And we're mostly just going to plug in our numbers. With one notable exception, our entropy is in units of joules, and it needs to be converted to kilojoules because delta H is in kilojoules and delta G is in kilojoules. From here, we're just going to solve it, and I'm going to skip ahead. The answer is 173.3 kilojoules. The sign is positive. Is this reaction thermodynamically favorable at this temperature? So basically, we want to look at the sign of delta G. That's what we really cared about. What is thermodynamically favorable? Is it a negative delta G? Is it 0? Or is it a positive delta G?
Negative.
Negative. So thermodynamically favorable, we would want to be negative. So this, we're going to say, no, it is thermodynamically unfavorable.